Imagine standing on a powder-soft beach, but instead of the postcard-perfect deep blue ocean you expected, you're gazing at a swirling, mystical, almost electric emerald green. This isn't a scene from a fantasy novel. It's the very real, scientifically fascinating phenomenon of tropical coasts with emerald green waters. And the reason it happens is not just about reflection or simple depth. It's a complex, living cocktail of physics, biology, and geology playing out on a colossal scale. Most people see a blue ocean and think it's just water, but that emerald hue is a giant, flashing neon sign pointing to a hidden world of immense productivity and ecological drama happening right beneath the surface. The journey to understanding this color starts with a fundamental question: why is any ocean blue at all? Sunlight, as we know, contains all the colors of the rainbow. When it strikes the ocean surface, water molecules absorb the warmer, longer wavelengths of light, the reds, oranges, and yellows, much more efficiently. The shorter, cooler wavelengths, specifically the blues and violets, are scattered and reflected back to our eyes. In the deep open ocean, far from land, with very little in the water to interfere, this scattering creates that iconic, profound sapphire blue. It's the color of pure, deep, nutrient-poor water, often described as a marine desert because its clarity comes from a lack of life-giving particles. But bring that water close to a tropical coast and everything changes. The first and most obvious agent of change is sediment. Tropical islands and coasts, especially those born of volcanic activity like the Caribbean islands or the rugged shores of places like Hawaii or the Seychelles, are constantly being weathered. Rain, wind, and waves erode the land, carrying finely ground rock, soil, and mineral particles into the shallows. These particles, often rich in silicates and clays, are suspended in the water column. They are much larger than water molecules, and they interact with light differently. While water molecules prefer to scatter blue light, these suspended sediments are fantastic at scattering the entire spectrum, but with a particular bias towards the green and yellow wavelengths. This process, known as me-scattering, is the same reason our sky isn't violet, the shortest wavelength, but blue. It's about the size of the scattering particles relative to the light's wavelength. So in these shallow, sediment-rich environments, the blue light from the water molecules and the green-yellow light from the suspended sediments mix, creating that distinctive milky yet brilliant emerald green. You can see this effect dramatically in places like the Gulf of Alaska, where glacial flour, rock ground to a fine powder by glaciers, turns the water a stunning turquoise. But in the tropics, the warmth adds another layer. The warm water holds less dissolved oxygen than cold water, which influences the types of chemical reactions and biological life that can exist. Furthermore, tropical sediments often come from the erosion of limestone and coral, which are rich in calcium carbonate. This white, reflective material acts like billions of tiny mirrors underwater, further enhancing the brightness and light scattering effect, turning a deep blue into a luminous, shimmering aqua. But sediment is only part one of this story. It provides the canvas, but the true colorists, the artists that intensify and modulate that emerald green, are living organisms. And this is where the narrative shifts from a simple geological process to a dynamic, breathing biological system. The transition from the open ocean's blue to the coast green is not just a change in color. It's a change from a desert to a rainforest. The very particles that create the color are the foundation of an entire food web. So, while you're marveling at the beauty, you're actually looking at the lifeblood of a coastal ecosystem. But before we dive into that teeming world of microscopic life, we have to address a critical, often overlooked factor that makes the tropics special: the sun's angle. The tropical regions receive direct, intense sunlight year-round. This high-angle light penetrates the water column more effectively than the slanted light of higher latitudes. It illuminates those suspended particles from above, making them glow more brilliantly. It also provides the immense energy required for the biological engine we're about to explore. This combination, intense light, warm water, and a constant influx of minerals from the land, creates the perfect incubator. The emerald green, therefore, is not a static paint job. It's a live broadcast of activity. A calm, clear day might show a softer, more translucent green. After a heavy rain, rivers swollen with runoff might dump a massive new load of sediment, creating swirling, opaque emerald patterns that stretch far out to sea. This constant state of flux is a visual indicator of the land-ocean connection, a reminder that the coast is not a line, but a vibrant, mixing zone. Understanding this transforms the view from a mere aesthetic pleasure into a reading of the landscape. You begin to see the green as a map, brighter. More opaque areas hint at shallower waters or recent erosion. Gradients of color show current flows and mixing zones. You are, in essence, seeing the metabolism of the coast. And with that in mind, the emerald water becomes a doorway. It's a signal that we are leaving the barren blue and entering a zone of immense richness. But to truly grasp what that richness means, we must venture from the world of inanimate particles into the realm of the living, to the trillions of tiny organisms that don't just live in this green water, but are often responsible for its most intense and spectacular shades. This leads us to the true power players of the Emerald Coast, organisms so small you could hold millions in a drop of water, yet so powerful they can change the color of an entire sea, fuel global food chains, and even control the very air we breathe. If sediments provide the base note for the emerald green, then phytoplankton are the symphony. These microscopic, plant-like organisms are the primary producers of the ocean, the foundation of the marine food web, and in many tropical coastal areas, they are the secret ingredient that turns a mild aqua into a vibrant, glowing emerald. The term phytoplankton encompasses a vast array of species, but in the context of green tropical waters, a few key groups are the star performers. Diatoms, with their intricate silica shells, and chlorophytes, a type of green algae, are particularly important. They contain chlorophyll, the same pigment that gives land plants their green color. Chlorophyll's job is to absorb sunlight, primarily the red and blue portions of the spectrum, to power photosynthesis. The light it doesn't absorb, the green light, is reflected back out. Therefore, a dense concentration of phytoplankton acts like an underwater meadow, reflecting a massive amount of green light back to the surface. When conditions are right, abundant sunlight, warm temperatures, and a supply of nutrients like nitrates, phosphates, and iron, these organisms can undergo explosive growth called a bloom. A major bloom can turn a vast swath of coastal ocean into a dense, green soup, visible even from space. This is where the data becomes breathtaking. Satellite oceanography missions like NASA's MADIS and ESA's Sentinel-3 use sensors to measure ocean color precisely to calculate chlorophyll concentration. The data reveals that certain tropical coastal shelves, such as the Amazon River plume, which carries nutrients far into the Atlantic, or the shallow banks of the Bahamas, are perennial hotspots of phytoplankton productivity. Their chlorophyll signatures paint them emerald green on satellite maps, a direct visual link from a satellite orbiting hundreds of miles above to the microscopic layer below. But why are these nutrients available here and not in the deep blue open ocean? This is the critical twist. The open ocean is blue precisely because it is nutrient poor or oligotrophic. The life there is sparse. The tropics, with their warm surface water, create a strong thermal stratification, a warm, light layer of water sitting on top of a colder, denser layer. This acts like a lid, preventing the nutrient-rich, deep water from rising to the sunlit surface where phytoplankton need it. So, how do the coasts overcome this? The answer lies in the dynamic processes of the coastal zone. First, as mentioned, Rivers deliver a constant stream of weathered nutrients from the land, agricultural runoff, decomposed plant matter, and minerals. This is a direct fertilizer injection. Second, the physical shape of the coast itself matters. Shallow shelves, like the Great Bahama Bank, allow sunlight to reach the seabed everywhere, warming the entire water column and reducing stratification. More importantly, tides and winds constantly churn these shallow waters, a process called vertical mixing, which stirs up nutrients that have settled on the bottom back into the light. Third, there is a phenomenon called island mass effect. As deep ocean currents slam into the steep slopes of a volcanic island or a continental shelf, they are forced upward in a process called upwelling. This physically pushes that cold, nutrient-rich deep water to the surface, creating an oasis of fertility around what would otherwise be a barren island in a blue desert. The combination of these factors makes tropical coasts biological powerhouses. The emerald green you see is literally the color of life being manufactured at a staggering rate. Every molecule of oxygen produced, every gram of organic matter formed, starts with that green pigment capturing sunlight. This productivity ripples upward, whether dense clouds of phytoplankton or equally dense swarms of zooplankton, tiny animals that graze on them. These in turn attract small fish, then larger fish, seabirds, dolphins, and whales. The emerald water is a dinner bell for the entire marine ecosystem. It represents a convergence of energy, a bubbling cauldron of growth and consumption. However, not all phytoplankton blooms are equal or benign. Some species, under specific conditions of pollution and excessive nutrient input, a process called eutrophication, can form harmful alga blooms, HABs, sometimes called red tides or brown tides. These can deplete oxygen in the water when the algae die and decompose, creating dead zones, and can produce toxins that kill fish and shellfish and even harm humans. While these are often associated with different colors, red, brown, orange, they are a perversion of the same nutrient-driven process that creates the beautiful, life-sustaining green. The presence of a healthy emerald green coast, therefore, indicates a balanced system. Nutrients are available but not in gross excess. Productivity is high but not chaotic. It's a system in a state of fertile equilibrium. This biological layer also interacts with the geological layer we discussed earlier. Phytoplankton can even influence the sediment itself. When diatoms die, their tiny glass-like silica shells sink to the bottom, contributing to the seafloor sediment. In some areas over millennia, these deposits form thick layers of diatomaceous earth. Furthermore, the very clarity of the water, affected by the phytoplankton, changes how light penetrates and thus how we perceive the sediment's color. A bloom can make the water more opaque, softening the view of the white sand below, while clear water allows the bright seabed to shine through, contributing to a lighter, more turquoise shade. It's a constant, beautiful feedback loop. To stand on an emerald coast, then, is to witness one of the planet's most efficient energy conversion systems. Sunlight is being captured in organic molecules, are being woven into organic matter, and the entire complex web of ocean life is being fueled. This green is the color of conversion, of transformation. It is the visual signature of the ocean's lungs working at full capacity. Yet there is another, more subtle actor in this play of light and color, one that doesn't get as much attention as sediment or algae, but is utterly fundamental to the dreamlike quality of these places. This actor doesn't add color itself, but manipulates the light in a way that makes every other color pop with an almost supernatural intensity. It is the silent partner in creating that glowing, jewel-toned effect that makes us catch our breath. And to understand it, we must leave the world of particles and cells and enter the pure physics of light, to the role of the stage itself, the seabed. Beneath the shimmering surface of an emerald tropical coast lies the stage that amplifies its beauty, the seabed. While sediments in the water column scatter light, The bottom itself acts as a giant reflector, a canvas that bounces light back up through the water, intensifying and modifying the color in a process known as bottom reflectance or substrate influence. This is the final crucial piece in the emerald puzzle, and it explains why the same body of water can look dramatically different from one bay to the next. The most powerful reflector is white sand, particularly the iconic sugar white sand of places like the Maldives, the Whitsunday Islands in Australia, or the Caribbean. This sand is often not made of quartz, like most continental beaches, but of calcium carbonate. It is the pulverized remains of corals, shells, and marine skeletons of foraminifera, a type of plankton with a calcium carbonate shell, and fragments of larger creatures. This material is brilliantly white and highly reflective. When sunlight penetrates the clear, shallow water and hits this white seabed, it doesn't get absorbed. It gets scattered back upward in all directions. The reflected light has to travel back through the water column to reach your eyes, undergoing another round of scattering and color filtration along the way. The effect is a double illumination. You're seeing light that has come directly down and back, which gives the basic watercolor, plus a huge amount of light that has been bounced off the bright bottom. This bottom reflected light fills in shadows, reduces contrast, and creates that famous, luminous, glowing quality. It makes the water appear brighter, lighter, and more vibrant. Transforms a deep emerald into a luminous aquamarine or a brilliant turquoise, especially in the very shallow areas. The depth is critical. The principle of water light attenuation means that light is absorbed and scattered with every meter it travels. In very shallow water, say 1 to 3 meters, a tremendous amount of light reaches the bottom and is reflected back with minimal loss. This creates those stunning, almost surreal bands of bright, electric blue-green water along a shoreline. As the depth increases to 5, 10, or 20 meters, less light makes it down and back, and the color deepens into a richer, more solid emerald or royal blue. This gradient of color is a natural depth chart. Pilots flying over tropical atolls use these color variations to navigate and judge water depth. But the seabed isn't always uniformly white sand. This is where the complexity and artistry of nature come in. Seagrass meadows, which are vital nurseries for fish and habitats for creatures like sea turtles, have a dark, greenish-brown canopy. When you look at water over a seagrass bed, the bottom absorbs much more light than it reflects. The result is a darker, often greener or browner hue. The seagrass itself adds its own chlorophyll into the visual mix, but the dominant effect is the loss of that bright reflective boost. This creates beautiful patchy mosaics of color from above light turquoise over sand patches and dark emerald or jade over seagrass. It's a direct aerial map of the underwater habitat. Then there is the king of tropical marine ecosystems, the coral reef. A healthy coral reef is a kaleidoscope of colors, pinks, purples, yellows, and browns from the coral polyps and their symbiotic algae, zooxanthellae. This colorful tapestry also reflects light, but in a more complex, multicolored way. The light bouncing off a reef is not a uniform white, but a mixture of wavelengths. This can create localized areas of unique color in the water above, subtle shifts that a keen observer might notice. However, a reef is structurally complex, with deep shadows and crevices that absorb light. Overall, water over a reef often appears as a darker, more variegated blue or green compared to the blinding brightness over a sandy shoal. The composition of the sand itself also matters. Some tropical beaches have sand with a high iron content, giving it a golden or pinkish hue, like the famous Pink Sands beach in Harbor Island, Bahamas. This sand, made from crushed coral and foraminifera with red shells, reflects a warmer light, subtly tinging the overlying water with a golden emerald tone, especially at sunrise or sunset. The role of the seabed teaches us that the color we see is not just a property of the water, but a property of the entire system from the sun through the atmosphere, through the water column, off the bottom, and back to our eyes. It's an integrative phenomenon. This is why the same stretch of ocean can look different from day to day, even hour to hour. A calm, flat sea allows for smoother light penetration and clear reflection off the bottom. A choppy, windy day roughens the surface, scattering light at the interface and creating more surface glare or sun glitter, which can mask the subtler colors from below. The angle of the sun is also paramount. At midday, when the sun is directly overhead, light takes the shortest path through the water to the bottom and back, resulting in the brightest, most intense colors. In the early morning or late afternoon, the low-angle sunlight has to travel through much more atmosphere and hits the water at a shallower angle. More light is reflected off the surface, creating glare, and less penetrates downward. The colors appear softer, darker, and more muted, often with a silvery or golden sheen from the sky's color at that time. This daily cycle adds a temporal dimension to the Emerald Coast's beauty. Furthermore, the sky itself acts as a giant blue dome, and its light reflects off the water's surface, adding a blue component to what we see. A perfectly clear blue sky enhances the blue notes, while a sky dotted with white clouds reflect those bright whites, making the water's surface appear more dynamic and variable. This interplay between the seabed, the water, the sky, and the sun creates an infinite variety of scenes. It means that no two views of an Emerald Coast are ever exactly the same. It is a living painting, constantly being repainted by the elements. Understanding this turns passive sightseeing into active observation. You start to read the water. That dark patch is probably a deep channel or a seagrass bed. That incredibly bright, almost white area is a very shallow sandbar. That smooth, medium green expanse is a sandy bottom about 5 meters deep. The coast communicates its secrets through color. And with this understanding of the physical stage, the reflective seabed, we have built a complete picture of the immerse phenomenon, the physics of water, the geology of sediment, the biology of phytoplankton, and the optics of the bottom. But this beautiful, complex system is not static, and it is not invulnerable. The very factors that create this paradise are now under threat from forces both local and global. The emerald green is not just a color of beauty, it is becoming a barometer of health, and its changes carry urgent messages we can no longer afford to ignore. The mesmerizing emerald green of a tropical coast is a signature of a specific, delicate balance. It is a balance between clear water and life-giving particles, between sunlight and depth, between nutrient inflow and consumption. Today, that balance is being destabilized by human activity, and the changes in the color and clarity of these waters are some of the most visible, poignant indicators of the environmental stress our oceans are facing. The first and most direct threat is pollution and sedimentation from land-based sources. Deforestation, unsustainable agriculture, coastal construction, and poor land management accelerate erosion far beyond natural rates. Instead of a gentle, constant trickle of fine sediments that create the classic emerald hue, heavy rains now wash massive, choking loads of mud and silt into the sea. This creates dense, brown, opaque plumes that can smother coral reefs, block sunlight from seagrasses, and devastate ecosystems. The emerald green turns to a murky brown not from productive phytoplankton but from lifeless dirt. This is a corruption of the very process that creates the color. Furthermore, this runoff often carries not just soil, but chemical fertilizers, pesticides, and untreated sewage. These are hyper-concentrated nutrient sources that fuel the wrong kind of growth. They can trigger massive, unbalanced phytoplankton blooms, the harmful algal blooms mentioned earlier. These blooms can be so dense they turn the water a soupy green, brown, or even red, but this is a green of sickness, not health. As they die and decompose, bacteria consume all the oxygen in the water, creating hypoxic or anoxic dead zones where fish and other marine life literally suffocate. The beautiful, life-filled emerald water becomes a silent, toxic, and lifeless zone. This is eutrophication in action, and it's a growing problem for coastal areas worldwide. Satellite data now actively tracks these events, and the maps show alarming increases in the frequency and size of such blooms near populated coastlines. The second major threat is climate change, which acts as a pervasive stress multiplier. Rising sea temperatures are a death sentence for the coral reefs that are often part of these tropical coastal systems. When water gets too warm, the symbiotic algae zooxanthellae that live inside coral polyps and give them color and food are expelled. This leads to coral bleaching. The coral turns ghostly white. Widespread bleaching events, like those that have devastated large portions of the Great Barrier Reef and Caribbean reefs, kill the coral. Without the living coral, the reef structure begins to erode. The bright, colorful reflector becomes a gray, rubble-strewn wasteland. This changes the bottom reflectance dramatically, often darkening the water above. But more insidiously, the death of coral reefs removes a critical barrier that protects the coast. Healthy reefs dissipate wave energy, protecting the shoreline and the delicate seagrass beds and mangroves behind them. Their loss leads to increased coastal erosion, which in turn dumps more sediment into the water, creating a vicious cycle of degradation. Ocean acidification, the other arm of climate change, driven by absorbed atmospheric CO2, also attacks the foundation of these systems. The increased acidity makes it harder for corals, mollusks, plankton like foraminifera, and many other creatures to build their calcium carbonate shells and skeletons. This threatens the very source of the white sand that creates the bright reflective bottom. Over time, acidification could fundamentally alter the composition of the seabed and the organisms that live there. Then there's sea level rise. As sea levels increase, they slowly drown coastal features. Shallow sandbars and seagrass meadows that thrive in specific depth ranges may find themselves in water that is too deep for sufficient light to reach them. They could die off, again changing the reflective properties and ecological function of the area. The emerald coastline of today might become a deeper, darker blue coastline of tomorrow, not by natural progression, but by forced, rapid change. The cumulative impact of these threats means that the emerald green is becoming an indicator species in itself. Its persistence in a vibrant, clear, and luminous form is a sign of a relatively healthy, resilient coastal system. Its shift towards murky brown, dull gray, or unnaturally dense, opaque green is a flashing red alarm. Scientists are now using sophisticated ocean color satellites, not just to study beauty, but to monitor health. They track chlorophyll anomalies that signal harmful blooms, measure turbidity, water cloudiness from sediment plumes, and even assess coral reef cover by analyzing the subtle light spectra reflected from shallow waters. This data is unequivocal. It shows that the most pristine, brilliantly colored emerald waters are increasingly found only in remote, uninhabited, or highly protected areas. Near human population centers and areas of intensive agriculture, the signals of stress are clear. This presents us with a profound responsibility and a critical choice. The Emerald Coast is not just a pretty backdrop for a vacation photo, it is a functioning ecosystem that provides immense value. It supports fisheries that feed millions of people. It provides protection from storms through its reefs and mangroves. It drives tourism, which is the economic lifeblood of many tropical nations, and it plays a role in carbon sequestration. Phytoplankton absorb CO2, and seagrass meadows are incredibly efficient at capturing and storing blue carbon. To lose these coasts is to lose biodiversity, economic stability, food security, and a natural climate buffer. The change in color is the canary in the coal mine. It is a visual, undeniable report card on our stewardship, but this is not a hopeless narrative. The very fact that we can understand the science behind the color means we can also understand the path to it. Preservation. The emerald green is resilient. It can recover if given a chance. And this leads us to the final, most important part of our journey, what we can do. The solutions exist, from local conservation to global policy, and every single one of us has a role to play in ensuring that future generations can also stand in awe of a thriving, glowing emerald sea. The story of the emerald tropical coast is a story of interconnectedness of land and sea, physics and biology, beauty and function. We've seen how it's created and what threatens it. Now, we arrive at the most crucial chapter, the chapter of action. Protecting these places is not an abstract environmental goal. It is a tangible, necessary endeavor to preserve the health of our planet and our own well-being. The good news is that the science gives us a clear blueprint. The first line of defense is the protection and restoration of coastal ecosystems on land. Since the quality of the water is so directly tied to what washes off the land, we must safeguard the natural filters. Mangrove forests are superheroes in this regard. Their dense, tangled roots trap sediments and pollutants from rivers before they reach the sea. They act as a natural water treatment plant. Restoring mangroves where they've been cut down for aquaculture development is one of the most effective ways to clear coastal waters and protect shorelines. Similarly, protecting wetlands and enforcing strict regulations on agricultural runoff and industrial discharge are essential. This means supporting sustainable farming practices that reduce fertilizer use and soil erosion. It means investing in proper wastewater treatment infrastructure for coastal communities. On an individual level, it means being mindful of what we put down our drains and what chemicals we use in our gardens, because ultimately everything flows to the sea. The second critical action is the creation and robust enforcement of marine protected areas, MPAs. MPs are like national parks for the ocean. They restrict destructive activities like dredging, certain types of fishing, and coastal construction, allowing ecosystems to recover and thrive. Data from around the world shows that well-managed MPAs lead to clearer water, more abundant fish populations, and more resilient coral reefs. The water inside a thriving MPA often looks noticeably different, more vibrantly colored, and full of life compared to overfished, stressed areas outside its borders. We can support this by advocating for the expansion of MPAs, choosing to visit and support ecotourism operators who respect these zones, and by being responsible visitors ourselves, not touching coral, using reef-safe sunscreen, as certain chemicals can harm coral and phytoplankton, and not littering. The third pillar is the global fight against climate change. The existential threats of warming and acidification can only be tackled by reducing our carbon footprint. This is a systemic challenge that requires transitioning to renewable energy, increasing energy efficiency, and protecting carbon sinks like forests and seagrass meadows. But individual choices aggregate into powerful collective force. Reducing our energy consumption, supporting clean energy policies, making conscious transportation choices, and reducing meat consumption, as livestock production is a major greenhouse gas emitter. All contribute. Furthermore, supporting organizations that work on blue carbon projects, protecting and restoring seagrasses, mangroves, and salt marshes directly helps the ocean's ability to sequester carbon and buffer against climate change. The fourth area is science and citizen science. We need continued research to monitor the health of these systems. Satellite data is powerful, but ground truthing is vital. This is where anyone can get involved. Programs exist where divers, snorkelers, and even beachgoers can report water clarity, note coral bleaching, log fish sightings, or monitor for algal blooms using simple smartphone apps. By contributing data, the public becomes a global network of ocean observers, greatly expanding the reach of formal science. This democratization of monitoring is powerful. It creates a personal connection to the water and turns observation into stewardship. Finally, there is the power of awareness and storytelling, which is exactly why we made this video. Understanding why the water is emerald green transforms it from a mere backdrop into a character, a living entity with a story to tell. When you understand that the color signifies a thriving food web, you see it differently. When you understand that a change in color can signal distress, you become an advocate. Share this knowledge. Talk about the science behind the beauty. When you post a picture of a stunning tropical beach, add a caption about the phytoplankton or the white carbonate sand. Shift the conversation. From "isn't this pretty" to "isn't this incredible and important?" Demand that your policymakers prioritize ocean health, support sustainable seafood choices, and consider the environmental impact of your travels. The Emerald Coast is a gift, but it is not a given. It is the product of a precise and miraculous balance. For centuries, it has inspired awe and wonder. Now, in our age, it needs more than our admiration. It needs our protection. The call to action is embedded in the very color we find so captivating. That green is the color of life, and it is asking us to help it live. So what can you do right now? Start by making this knowledge active. If this video changed how you see the ocean, your first and most important step is to share it. Click the share button right now and send this to one person who loves the beach or who needs to understand why the ocean matters. Place it on your social media, in your family group chats. Let's spread this understanding far and wide, because awareness is the seed of action. Secondly, subscribe to this channel. We are dedicated to uncovering the hidden stories of our planet, to turning wonder into understanding and understanding into empowerment. By subscribing, you join a community that values this knowledge, and you ensure you don't miss our next deep dive into the world's wonders. We have videos coming on coral reef secrets, the deep ocean, and how other incredible natural phenomena work. Your subscription tells the YouTube algorithm that this content matters, helping us reach more people. Thirdly, engage below. The conversation is just as important as the video. In the comments, tell us, have you ever seen an emerald green coast? Where was it? Did you ever wonder what caused the color? Now that you know, will you look at it differently? Share your stories, your pictures, your questions. Let's build a community of curious, informed ocean advocates right here. And finally, carry this knowledge with you. Be a guardian of that emerald sparkle. Whether you're thousands of miles from the coast or standing at the water's edge, remember that the choices you make, what you buy, what you eat, how you vote, what you share, ripple outwards. They can contribute to the murky brown of pollution or support the vibrant, life-filled emerald of a healthy sea. The ocean is not separate from us. We are interconnected. Its health is our health. Its future is our future. So let's be the generation that not only marvels at the emerald secret, but also becomes the generation that fiercely, intelligently, and passionately protects it. Thank you for watching, for listening, and for caring. Now, let's go make a difference.